Okay, so let's get started. Today is going to be a bit of procedural stuff where I ask you to actually calculate some things. But it's also a topic which is not paid much attention to in physics and happens to be very important. And as I went around looking at your graphs and the way you have calculated things and all that, I suspect that many of you don't pay much attention to this aspect of uncertainties in physics. Okay, so I'm not going to talk about anything quantum mechanical or anything like that. So this is very mundane kind of uncertainty we are doing in the experiments today and yesterday. All right, although I suppose the ideas sort of carry on to that realm as well. So where should I point this? Oh, this way, okay. Oops. Okay. Okay, so here's the, perhaps many of you will recognize, that Archimedes was given this task to find out whether something was gold or not. So if you want to find out if this metal that you are given is gold or not, typically you do a density measurement, right? So let's say you know to some accuracy what is the density of gold, then you can find the density of your material and then compare it with this. So this piece of gold was given to two people, George and Martha, because those are the names which are there in the textbook that I was looking up. So you can look at what's going on here. Basically, George gives a measurement which is around 15 gram per centimeter cube, but then also says that it can be anywhere between 16.6 gram per centimeter cube and 13.4 gram per centimeter cube. Right? So maybe George was right and did his measurements well, but this is what the outcome was. And it seems like Martha has a different value. The estimated value is different. And she reported whatever 13.8 gram per centimeter cube and also gave some sort of margin of error. So who would you believe is the question, right? So George's measurement, while it may be accurate, you can never be sure whether it is gold or some other alloy, because both gold and the alloy, their densities sort of lie within the margin of error that George has presented, right? While Martha seems to have a lot of confidence and says that, look, the uncertainty in her measurement is very low. But if you make a claim like this, then it has to be supported by some other measurements. How sure are you that this is the uncertainty? So yeah, I mean, if it was me, I would take Martha's measurement, provided she did some more experiments. What about you guys? What do you think? So if both of them came to the manufacturer and just gave the mean values, then what do you think the manufacturer should do? Yeah. So if you do not provide a number which tells you how accurate or how good a number is this, then a best estimate of a number is quite meaningless. That's what this kind of shows. If George just said it is, say 14.8 gram per centimeter cube without any margin of error, then I would think that, oh, maybe it is gold because it's close to that. So that measurement becomes meaningless if it is unsupported by some margin of error. Is this right? And this is something, I mean, whatever I'm going to talk today is actually absolutely common sense. And sometimes even there's no pakka rule to it or something. You have to use your senses. There's an art actually to finding out uncertainties, but most of the time common sense works. So if I was a manufacturer, I would not believe what George said, even if the value is closer to gold, and however much I would want to believe what he says, I probably would not. Okay, so just to reiterate the point, there's no measurement which is actually free of any uncertainty. You know, you might want to, I don't know, you might be a car, like you might want to build a board which is as big as this room, like this one, right? So you can measure the length of this board and you have a meter stick, you measure it, you get some uncertainty, and you might be a total perfectionist and you want to measure it. Great, you might become obsessed with the idea of having a perfect measurement, right? So maybe you don't have you have a screw gauge that gives you some uncertainty. Maybe you go and build an interferometer, but even that will have basically a length scale which is determined by, minimum length scale which is determined by, I suppose, the wavelength of light. So, you know, so you can keep on doing this, right? But then you are never going to get a perfect number. So it might seem obvious to say this, but there is basically anything you do comes with some uncertainty, right? So an experiment, for example, is never complete without reporting the uncertainty correctly or reporting an uncertainty, okay? So if you look at, these are the kind of terms that are typically used in you know, qualifying the amount of doubt we have in a measurement. There's accuracy, precision, confidence, uncertainty, etc. And you know, to a layman, it might seem that they're all kind of related, and they are. But there are some well-accepted terms which are supposed to mean some things. So accuracy is typically what we call the closeness to our measurement to what is known to be a true value. So if you know the actual value of density of gold and you go and measure it and it happens to be close to it, then it would be an accurate measurement. However, that is, you know, that's only if you know the actual value, and often we don't have that information, right? Most often we do not have that information. Of course, these days we have a lot of information. It's at the tip of our fingers. But yeah, if you want to appreciate an error analysis, you have to go back to analog and pre-internet days, because they had to do this. They did not have the internet to check up on, you know, what was what. So precision is, you know, what you would call the closeness of repeated measurements to each other. So if you are able to measure, if the measurements are close to each other, closer to each other, then I don't know, I suppose you could compare it with another measurement, then it would be a more precise measurement. Uncertainty is something that we talk about a lot today. It's basically a number that you give to how much doubt you have in a measurement. And a measurement also has to typically come with a confidence value. So how confident are you that your estimate that you are making is close to the true value, okay? So we won't talk that much about confidence today, but just keep in mind that there is this extra thing. So this picture is actually representing exactly that. An accurate measurement. So in the first figure, we have an accurate measurement which is not necessarily more precise than the second figure. In an accurate measurement, you're actually hitting the bullseye, but then the spread is there between individual measurements. In a precise measurement, you have these very close to each other points. However, it is missing the mark by quite a bit. But you wouldn't know that when you're doing an experiment. Yeah, and confidence is basically the spread is related to the spread of the different measurements that you make. Okay. Yeah, of course. Yeah. That was just to show you that they are not necessarily this related to each other. They could be independent. Okay, so when you measure something and then you want to report it, like in a lab report or in an experiment, paper, whatever, the respectable way to do that is not to just to give an estimate of what you think the measurement is, but also give what is the uncertainty and with what confidence do you say that this is the estimate. Okay, so a complete measurement would have all of these different quantifications. One is the best estimate of the measurement, then there is an estimate, quantification of basically the uncertainty of that measurement. So you're saying that, look, this measurement, this length lies somewhere between 10.4 and 10.6 centimeter, okay? And at 95% confidence level, that means that 95 out of, I mean, of course, you have to do it a number of times, but I'm saying the probability of finding that measurement, finding of any measurement being within this interval is basically 95%, okay? Is that clear? Okay, so let's just unpack each of these things and try to get a better feel of all of them. These are just some definitions. I'm just repeating the closeness of repeated measurements to each other as precision. And precision can be, of course, influenced by various factors. Those of you who are doing the Kibble balance who will know that precision of your experiment is dominated by what? The instrumentation resolution, right? The resolution of the instrument itself. So there is that least count which is sometimes dominates the precision. But often you can do the same experiment a number of times and you do get the same value to within the least count. So whatever variation is there might lie within the least count, right? And often you might get variations which are much larger than the least count. So for example, the other day, Rajaram was telling us how the unit of length was set and that there were several platinum rods all over the world, and one of the big sources of error was just thermal expansion, right? So that's a huge source of variation. So all of those factors, environmental factors, can also determine the precision of your measurement. But I mean, being a college teacher, I have now, I mean, earlier I used to be a lot more relaxed, I suppose, but now I am a little bit, I have developed a, I've developed an aversion for measurements being reported with too many significant figures. So I just want to point out some of the mistakes that I often find that students make while reporting precision. So when you report a measurement, an estimate, your best estimate should always reflect the precision of the measurement. You can't have a reported measurement which looks overly precise. You might have taken 1,000 readings and divided by 1,000, okay? That doesn't mean that the precision becomes 0.001, right? So it should reflect the precision of the instrument, okay? So let's just do a little exercise. I have these 4 different kinds of scales, and I have an object of the same length being measured by all of these 4 scales. So if you were to measure the length of the object using the first scale, then what would you say is the length of the object? 10 centimeters. And what kind of margin of error would you give? 1 centimeter, right? But that error is basically centered around 10 centimeter. So you would say that the real value, this value is lying somewhere between 9.5 and 10.5 centimeters. If it was above 10.5, you could see it and you would actually round it off to 11, right? Again, this might seem obvious, but it's worth reiterating and remembering that these things are also important while doing measurements. What about the second one? Okay, 10.5 would be the rounded off number, right? Plus minus 0.25. So you have 10 and then you have 10.5 and the third one gives you? Yeah, so now it gives you 10.4 and the last one gives you? 10.3, right? So as you include more and more divisions, you're getting to be more and more precise with your measurements. Okay, there's nothing, there's no Nobel Prize winning stuff over here. It's very simple, but often overlooked. So, yeah, sorry. Yeah, so when you report this measurement, if I use that scale and report 10.3, then would that be okay? No, it wouldn't be okay, because the way you report it should reflect really the precision of your measuring instrument, right? So, yeah, that's something that I wanted to say. So often we have these kinds of issues where you're trying to, in an experiment, you have multiple measurements and you're trying to report some sort of number which is basically comes from a combination of these different measurements. So let's take an example of velocity measurement, for example. Okay, so maybe I get chalk. So in a velocity measurement, you have a stopwatch and you have some sort of scale, and maybe you're looking at an ant which is moving on the scale or something like that. And your scale has a least count of 0.1 centimeters, and your stopwatch has a least count of 0.1 seconds. So this is what is given to you. Okay, so now we have to just look at these numbers and decide which of these reported numbers would sit right with us. Okay, would reflect the precision of the measurement. So in the first case, we have a large length and a small time. So 12.4 and 12.4 centimeters is covered in 0.5 seconds. So would I, what is it? So I have 4 options. Okay. So 24.8 centimeters is what you have decided. Let me just write down the answers here and then we can discuss why you said that. Okay. How do you know it's C? It can only have 0.1. That's your intuition. Okay. We can talk about it. It can be B as well. 180. Okay. Okay, so somebody says B as well. This is centimeter per second. We'll discuss this. Right. And what about the last one? A. Okay. A? D? Okay. So there are 2 options, A and D. I mean, I made a face when I said A, so people must have thought, oh, that can't be right. So A is telling you that the velocity, the best estimate of velocity is 0. Okay, but you have made your estimates or your measurements of time and length within the experimental accuracy, right? So there's got to be some rule. There's some, I think I would believe 0.003 more than I believe 0. Okay, right? So there is a rule of thumb, of course, which is actually a heuristic more than a rule. I mean, I don't think anyone has gone and proved it. But they've said that, look, this is the kind of thing which actually reflects the precision of the measurement. And you have to make sure that when you report the measurement, it should reflect the number of significant figures in that number which has the smallest number of significant figures. Okay, so all of you are familiar with significant figures, right? I am not. I'm familiar, but I keep faltering with this. Huh? Everyone knows what significant figures are? Yeah, all these things that we learn in school and we think have been buried, they will suddenly show up again. Okay, so the rule of thumb is that, so I told you what the rule of thumb is. That, when you have a combination of such measurements, you would basically write the reported measurement in such a way that it reflects the least number of significant figures, that measurement with the least number of significant figures. Okay, so let's see, what is the first one? First one is 24.8. Is that fine? How many significant figures does 0.5 seconds have? 1, yeah, it has 1. What about 12.4? 3, okay. So the answer should basically have one significant figure. So 24.8 is acceptable. What about, so for the same reason you have 1.2 being the, so what is the number of, no, what is the number of significant figures in this? 10.5? 3. What is the number of significant figures in 12.4? 3. So by this rule, what do you think should be the? 1.18 should be okay. That somehow doesn't sit right with several of you. I noticed that. Is there a problem with it? Because we are not measuring length. We are measuring velocity. It's a combination of two measurements. When you divide it, the precision, I mean, you can actually get more decimal places than are allowed by a single length measurement. It's not as if you are covering x in 1 second and that's all you're measuring, right? So in this case, you have actually a velocity which is of the order of 1. Time and length are roughly same numbers, order of 1 meaning 1 centimeter per second, I should say. Okay, so yeah, I mean, it's a good question. Let's put a pin in it and maybe over time you'll grow to accept the answer. What about 3? How many significant digits are there in the first? 4. Okay. What about 0.3 centimeter? 1. So which of these has one significant figure? Yeah, D has one significant figure. So this goes to show, in such cases when you have an extremely slow velocity, you might have the ant actually moving. It doesn't mean that without these, with these scales, you cannot make a measurement of the velocity, right? You may have a scale which only measures 1 centimeter per second, and you might have a watch which only measures 0.1 second, sorry, scale only 0.1 centimeter. But you can still make a measurement of velocity of a very slowly moving creature. You have to give a lot of time, 100 seconds. It's not wrong, isn't it? Why should be wrong? So this is what I'm saying. There's no rule. You will have to decide what is correct and what is wrong according to the measurement that you have made. So just because there are many, I knew there would be several people who are not familiar with significant figures. I added this slide just as a recap. So basically the definition of significant figures is in a measurement is the number of digits which are known with certainty plus 1 which is an estimated digit. So like if we said, you know, it is 10.5 centimeters, then that 0.5 is actually estimated because it's closer to 10.5 than 10, right? That has, you're absolutely right, yeah. That has actually 3 significant figures. That's right. That you are right. Thanks for pointing that out. So then what's the answer? Yeah, so 20 is actually, we don't know it more accurately than 20. And that's because a large length is being covered in a short amount of time. Right? So the time in the denominator is probably overestimating, the small time in the denominator is probably overestimating the value of the velocity. Okay, so you're not sure that it can be that high. You're absolutely right. Thanks a lot for pointing that out. Yeah. Let's just look at this before we get. Okay, so non-zero digits are always significant. That's a no-brainer. Any zeros between significant digits are also significant. Any leading zeros are not significant. So 0.12, etc. will have only 2 significant. Trailing zeros in a decimal number are significant. What does that mean? So the 0.0 is reported with confidence, and that means that, oh, that is a significant thing. Yeah. So why wouldn't you say it's 4 significant figures and only 2? Is it 4 or 2? 100.0? Yeah. So you would say, I would say that it has 4 significant digits. So you are actually confident about 100, and the last one is an estimated value. No. That because you're reporting, that's what I'm saying. This is not maths. This is optics. This is more like how to report. You want to report something correctly. As an experimentalist, you have these are tools of the trade, and you have to learn all these things. So if you want to say, look, it is 100 point, if you say it is 100.0, then whoever is reading it will assume that, oh, that 0 after the thing is also important, it's significant. Yeah. So when you are reporting 100, what you are, this is the sort of lore of significant figures. What you are saying is that you have rounded it off to the nearest hundreds. So that's why it has one significant figure. I don't know if there is there some science to this? I should ask.
No, it's just a convention.
It's a convention, yeah.
But if our instrument is able to measure it with a certainty of 0.1,
yeah,
then when we are reporting the velocity also we should report it with a certainty of like till 0.1 decimal.
Why? Because time is measured with a different thing and length is measured with a different thing.
So both of them have like 1 decimal digit in their measurement.
Yeah.
So when we are reporting, we can have like 1 decimal digit in the least count of both of them is like till 1 decimal digit. So when we are reporting also, we should be able to report it till 1 decimal digit, right? Because
you should be able to, but then there are several reported measurements which have more than 1 decimal.
So then we'll round them off.
No. Like 003, for example, in the previous case where we looked at this last one, 0.003. That is a measure. That's the measurement that I would think is relevant.
The second part, if you see, like we have up till 1 decimal digit that we can do the measurement. So that is why when we're reporting also, we should have only 1 decimal digit while reporting, right? That is why we can't use 1.5.
Yeah, okay. No, I get it, yeah. But see, you're losing out a lot of information if you do that in every single measurement. For example, if something is really moving slowly, then you will not be able to report any velocity, You will always say 0 because you're never going to be able to get any. So you want to report something, and then perhaps you can find out what is the uncertainty within this measurement. Okay. So basically what I'm trying to say is, how do you report it in a clean and sort of polite way so as to tell the reader that there is some significant measurement here, but not imply that, oh, it is overly precise, okay? And not also cut out useful information. So this is why we have these rules. These rules are here for a reason. Okay. And a lot of times people don't like it because it's like this.
Can I make a comment here? No, hello? Yeah, while the people were doing the experiment yesterday, there was a place where they measured some number, and that was the tan of some angle.
Yeah.
So they punched in the number into the thing, and then they got the angle, and they were writing down all the digits on the calculator.
That's right.
Right? I think that's definitely not a good experimental practice, right?
No.
Yeah. I just wanted you to comment.
Yeah. No, so there you will have to find what is tan of an angle. Tan of an angle is basically the ratio of two lengths, right? So you might, I don't know how you guys found theta. I think you found the lengths, isn't it?
Ratio of two lengths.
Ratio of two lengths. So then the uncertainty in theta, sorry, the precision of theta would depend on the precision of the length measurements. The one which is less precise, that would dictate really the precision of theta. The precision of tan theta, no, that is the precision of tan theta, yeah, isn't it?
Yeah. And then the theta, when you take a tan inverse,
Yeah.
the calculator is giving you a lot of junk.
Correct.
Yeah, so you should know that that is junk and
Yeah.
not write it down.
Yeah, so that's typically what I see in several AB records, especially because, people do their data analysis on, using calculators or like Excel or something, and that gives you a whole string of digits beyond the decimal point. And students, being very conscientious, want to take all of those digits and report very honestly what they have got. But all that stuff is junk. You should discard it. And you should make a decision about what is the precision with which you want to report your measurement. Okay? This is the point I wanted to get across first. So yeah, just in case you didn't know this, addition and subtraction of two numbers, basically the sum should have the same number of decimal places as the fewest decimal places. Okay, and similarly in multiplication and division, again, you will choose the result to have the same number of significant figures as the lowest, the measurement with the lowest number. So this is the sort of, okay, so now we come to uncertainty. We just talked about precision, which has to do more about, I told you that a measurement has several parts, right? There's an estimated part and there's an uncertainty and there's a confidence and all. What we talked about till now is basically to do with the estimated part. And what we are going to talk about now is the uncertainty, which you guys are now you've started to calculate it in your, for your experiments, right? So this is something that would be relevant. So as we know, uncertainty is, I'm sure all of you know, that it's basically a quantification of our doubt in a measurement. And if I tell you that the uncertainty is delta x, then, and the value is x, then what you're saying is that if you make a measurement, your value, the value that you measure is going to lie somewhere between x minus delta x and x plus delta x. So that is what we mean when we give this value delta x as the uncertainty. Okay. However, we don't know for sure that every measurement we make is going to lie only in that interval. You will have to make a lot of measurements if you want to find that all measurements lie. So we choose a more sort of relaxed position, saying there is a high, we sort of quantify the probability with which a measurement should lie within x plus delta x and x minus delta x. Okay. So for example, if you guys are familiar with calculating the standard deviation, that means that most of the time, 68% of the time, a measurement would lie between x plus standard deviation and x minus standard deviation, right? Okay, so these are some of the things that we need to sort of, these are the things that we keep at the back of our mind, often forget. So it's sort of useful to remind ourselves. So this is just a definition. So let's learn how to report uncertainty. Just as we reported the estimate, the best estimate, how does your precision, measuring instrument, etc., determine how you report the uncertainty? Okay. So if I looked at something like this, you cannot look at this report of, this is the number given as G. Okay, and this was from one of my lab reports. Don't tell anyone, Medha, using this. She's not here. She's here. Oh, there. Okay, so this is from one of our lab reports. Obviously, is this okay? What do you think? When you see this, what does it make you feel? It has very less uncertainty. Okay, anything else? The measurement is too precise. Why? Maybe the measurement is precise. Yeah, okay. So maybe it is a precise measurement though. If it is, then what is wrong with reporting it this way? Is there something wrong? Yeah, go ahead. Why don't you finish your answer?
9.82 seems not seems like if the instrument is as precise that it can measure up to that much
Yeah.
decimal places, then 9.82 does not seem like a.
That also should have had several more things, right? Significant figures, but yeah. So your uncertainty and the reported estimate cannot have such widely varying precisions. The uncertainty, the acceptable thing is it has one more, this is an acceptable, again, rule of thumb, one more decimal place than the estimate. Okay, so here in this case, you have 9.82, which is reported with 3 significant figures, only 2 numbers after the decimal point. And then you have this uncertainty, which is extremely precise. Okay, and of course, your calculations when you do x minus xi square and by n, you might get numbers which have lots of decimal places. But you have to know where to truncate this. So how would you write this? What is a good way to write this, report this measurement? Point 0.03? Okay. 9.82 plus plus minus 0.03. Okay, yeah, that's acceptable, right? Because in my main measurement, I have 9.8 being the ones I'm sure of, then the last one is I'm not sure of. But I know that I can add maybe 0.02, subtract 0.02, and that is what my uncertainty is.
Also here, don't we have to consider significant because 9.82 has 3 significant figures.
Yeah.
If we consider 0.003.
No. No, we are placing everything on the same sort of, so basically the uncertainty affects the, what place, hundredths place, right? It's not about significant figures here. Yeah, that's true, but I'm not able to say exactly why. Do I not need to go? Okay, let's talk about that maybe. I'm not sure.
As of now, is it like if we measure a value and if the number of decimals of that value is x, then the same number, the uncertainty should also have the same number of decimals.
Yeah, it should have the same order of magnitude as the last decimal. So that's what the second thing says. The last significant figure of the estimate has to be the same order of magnitude as the uncertainty. Okay, so what does that mean? The last significant figure of our estimate in the first line is 2, that 2 thing there, and that has an order of magnitude 10 to the minus 2. So your uncertainty should also be the same, roughly the same. It can have 1 order of magnitude lower if you have done, if you think that is important. Okay, so there is this leeway here where if you think it is important, you keep it. Okay, so how do you rewrite the second one? 6051.78 plus minus 30 meters per second. 6050 plus, absolutely. Why not 6051 plus minus 30? Oh. Okay.
But just before we said we don't have to consider the significant.
What if it was 29 and not 30? Okay. Okay, yeah, all right. So yeah, 30, if I put a point and a 0, then one is happy. What about the last one? So here I just wanted to say that, this is a very bad way to report any measurement, okay? Where the estimate has 1 order of magnitude and the uncertainty has a whole different order of magnitude. Ideally, you would want to put them both with the same order of magnitude. So your 3 has to be written as what, 0.000, how many zeros? 0.0003 into 10 to the 4, right? So you see that the uncertainty is affecting only the number which is 4th after the decimal place. So So I can write this as 3 point, should I truncate the estimate? Is that okay? 3.1234, is that okay, or it's too precise? It's too precise? No, it's as precise as the uncertainty allows me to be, right? So we know the uncertainty to the 4th decimal place. So the last digit, last significant digit of your main estimate has to be of the same order of magnitude. That's what it's saying. So I can keep 1, 2, 3, 4, all the way up to 4. Yeah. So if you were to keep the, if you wanted to change the uncertainty in the second one, then what would it become? You have, would you? Okay, yeah, I think I agree with that. Yeah, that's fine. But, you know, these things, they, it's confusing because, you know, there are all these ways and of people and how they write. So typically, if you omit a 0, it means you have truncated it to the last 10th. That's what my understanding. Yeah. Yeah, but perhaps you have measured the uncertainty very well, you know, to all the way up to the 2nd decimal place. That's also a possibility. Maybe those zeros are significant. If they are significant, then we should keep it as it is. But in this case, it is not significant because of the rules that we have all agreed upon of significant figures. Yeah. That's a good question. I don't know why we don't do that. We should do that as well. Because often actually it is a complicated answer. It's not just one instrument which is measuring your, you know, it's not usually like, okay, you're measuring some distance between interference fringes, maybe you're using micrometer or something. But often you have to multiply one thing by another thing and then find some complicated new thing. Okay, so we have to decide what is the precision of that combined calculation. Yeah. Don't try to generalize it. It's very specific and context dependent. So I would urge you all to like rein in those. I know that you all want to generalize and simplify, and don't do that. The number of decimal points, they should be of the same order of magnitude as the last significant digit. That is the crucial thing. Okay. Often, in fact, people will say you give the uncertainty to one significant figure and that is enough. All right, because it is affecting only the last decimal place of the main estimate. Yeah, you had a question. Yeah. I don't know. I don't know. I give up. Okay, let's move on. We live with that uncertainty. Okay. Okay, so I didn't know this, but when I was going through the literature, apparently for people who want to generalize and put in boxes, which is all of us, okay? There is these two types. So people have classified the kinds of uncertainties that we calculate. So type A evaluation is something that all of us are familiar with. We do a measurement, we repeat it a number of times, and then from that, we calculate what the uncertainty is. But often that is not the case in several experiments. You might have the chance to do an experiment only once. So then how? You cannot give a number without reporting the uncertainty. So you need to somehow estimate the uncertainty, okay? And you can do that by estimating, finding different sources of uncertainty and propagating it. There is something called propagating uncertainties, which I'll talk about shortly. So you will have to do some sort of jadugari to actually, and you will have to estimate using your estimation chops. So these are the two types. So type A evaluation, I'm going to just quickly go through because all of you are very familiar with this. This is something that we do all the time. Let's imagine we are measuring the length of a rod and it turns out to be like all of these different measurements, 10.5, 10.7, etc., etc. We know how to calculate something called the variance, right? And how do you understand? All of you know what the variance is? Has everybody been taught this in school? Have you learned variance in statistics? Okay. So basically it's the average deviation, the square of, you take the square of the deviation from the mean and you find the mean of that square of the deviation and take and so that is the variance, okay? But if you find just the mean, the denominator over here you'll notice has an n-1 and not n. So there's a reason for that and I'll tell you about it shortly. So yeah, so from this variation you can calculate something called the standard deviation, and the standard deviation is what we normally accept as the uncertainty of a measurement. So what it is telling us is that any new measurement you make would probably lie within the standard deviation with a probability of what? 68%, which is, what is the 68%? Where did I pull this out of? From the normal distribution. So what is this normal distribution? What is it about the normal distribution? Okay, okay. So yeah, so basically if you take a normal distribution and you take the mean and then you make a line, you draw a line about 1 sigma away from the mean and to the right and to the left, then the area under that curve will be 68% if it's normalized or not, okay? So basically it tells you, how much of the data is it covering. 68% of the data lies within that range. Yeah, so with all of this, the final result that you would say is basically 10.6 plus minus 0.1 centimeter. Why? Why is it 10.6 and not 10.58? No, the 10.6 is simply because the measuring instrument has that least count, okay? And yeah, I think you could round it off to one significant figure and leave it as 0.08 also, but depends. I'm okay with 0.08. I honestly don't know if there's a right or wrong answer to this. Till now, I haven't had the guts to ask anyone. I mean, I've asked, but everyone has given me wishy-washy answers. Okay, so often here in this case, we have found that the standard deviation is actually lower than the least count. And that happens, right? If the other variations are not there, if you're doing the experiment correctly, you keep on measuring the radius of your, whatever it is that you're measuring. It can turn out to be that every time you do the experiment, you get the same answer within the least count. Okay, so yeah, so a low standard deviation actually reflects that maybe you need a better instrument, but it also reflects that it is a precise measurement. Okay, so I would say that there is nothing wrong in leaving it at 0.08, but the textbook I was following rounded it off to 0.1. I think it's fine to leave it as 0.08 centimeter. Yeah. So the least count is not the uncertainty. If you do one measurement, the least count would be the uncertainty. But if you do several measurements, that is actually improving the precision of your experiment, right? So I think the value would be going closer and closer to some true value. And so the standard deviation becomes the more important thing. But oftentimes you don't have the ability to do this experiment a number of times. So then in that case, you may have no choice but to report the least count as the uncertainty. Yeah, that's what I said. I think you can keep the, keep one significant figure in the standard deviation and write it as 0.08 centimeter. All right, so I told you that there is this n-1 in the denominator, okay? And the fact that there is this n-1 denominator, maybe you thought about it, maybe, I don't know if you thought about why there is n-1. Or you questioned why that suddenly appeared n-1. Yeah. So when we do some measurement, we are doing whatever measurement we do, but that measurement may or may not be close to the true value, which is basically the mean of several measurements. Out of all of you measure alpha, out whatever surface tension, and put them together, and you would see that there's some spread, okay? And of all of that, there is some true value. Sorry, I don't know what. So that is the true mean, and this is the sample that we have. So the true mean lies here, and the sample mean lies here, okay? And when we are measuring uncertainty, we are using the sample mean, okay? So we are actually restricting all our points to be, to be spread out in such a way that their average is constrained to be that point. So all of these points are actually not independent, and they are constrained by this one equation which ties them to that sample mean, okay? So when you measure the, if you use just n and measure the standard deviation, use just n in the denominator and measure the standard deviation, you might get a small value. But actually the standard deviation is much larger than that, right? So it's actually, it's not a, again, it's a construction. I don't know who it is due to, but somebody famous. And basically, it's a sort of a heuristic to say that, look, if I want to estimate the standard deviation better, I need to divide by n-1 and not n, because I'm constraining all of these n points with this one mean. Okay, I'm tying it to this mean. So the number of degrees of freedom is reduced by 1. All right, so that gives you a closer estimate of the uncertainty, while just this sample standard deviation gives you a smaller estimate of the uncertainty. Doesn't give you a true, actually you're underestimating the uncertainty. Okay, so now here is the operational bit of all of this and what you guys have to do in your error analysis. Okay, very often, as we saw in that velocity thing, we are taking two measurements and we are combining them, right? So these two measurements have their individual uncertainties, and we combine them, then the result also has its own unique uncertainty. So how do we calculate the uncertainty in the result, right? And again, you might be familiar with several of these examples that I'm going to tell you. So let's imagine that you have this quantity Q, and it's actually the sum of two independent measurements, x and y. So this Q is equal to x plus y, right? And you want to find out what is the uncertainty in Q, right? I know the uncertainties in x and I know the uncertainties in y. I know that this is uncertainty delta x and this has uncertainty delta y. What is the uncertainty in Q? So just a simple argument would tell you the maximum possible value of Q would be when this value is at its highest and this value is also highest, right? So if I were to look at the maximum possible value of Q, it would be x plus y plus delta x plus delta y. And similarly, if I were to look at the minimum value, what would it be? What's the smallest value that you can get of Q if it had these uncertainties and this was basically the formula for Q? Yeah, so the smallest would be when both x and y are their smallest values. So it would be x plus y minus delta x minus delta y. Okay, so this simple argument tells us that, oh, maybe there is, I know that this is actually the best estimate of Q, and I can say that the best Q is equal to this best estimate, x plus y, plus or minus this delta x plus delta y. So, one way to report the uncertainty is just to add up the two uncertainties, and you would get something which represents the uncertainty of the sum. Okay, and you can actually test it out, and the same thing works with the difference. So if you had Q to be x minus y, then what is the maximum possible value of Q? What is the minimum possible value of Q? You can try and figure out, and then again you will see, what do you think the uncertainty is going to be? Is it going to be delta x minus delta y? Yeah, okay, so let's work it out. What is the largest value of Q? X plus delta x minus y. Huh? Should I write? Minus y plus delta y. Is this the largest or? This is the largest? Okay. And what is the smallest? Sorry. The assumption is that delta x and delta y are positive numbers. Okay, I didn't say that. X and y may be positive or negative, but okay. So x minus delta x minus y minus delta y. Right, so in both cases, again you see that the resultant uncertainty is just the sum of the two uncertainties. Okay, you see that? So when you add or subtract two independent quantities, the uncertainties tend to add up. This is a simplistic, this is for now, this is the answer. We're going to have another look at this answer. Okay, but actually it turns out that this is an overestimate of the uncertainty. If I say that the uncertainty is delta x plus delta y, then it's actually overestimating the uncertainty. Because why is it overestimating the uncertainty? They are the extreme points. It's extremely rare to actually be able to measure those, to get those extreme values. If you want to get the maximum value of Q, both x and y have to have their maximum values, okay? Which is a very rare event, right? So another way of actually finding the uncertainty is to calculate the root mean square like that. So instead of adding it up, you square the individual uncertainties, add them and take a square root. Okay, so now why this is the formula? There are several ways of understanding this. One way is if you know about Gaussian distributions, then basically you know that these measurements, uncertainties are independent of each other, right? So a combined probability distribution will be the joint probability distribution of the individual uncertainties. So if you have two Gaussians, one with a width of delta x and the other with the width of delta y, then the combined width would be square root of delta x square plus delta y square. This comes from basically, if you know a little bit more about the Gaussian, then this would be obvious to you, but I'm going to go a bit fast because I think I have a lot to do and then we haven't gotten anywhere. Obviously, this is a very confusing topic. Okay, so the same thing can be done for products and quotients as well. Okay, and there I'll leave it as an exercise to you. You can do the same kind of thing. So let's say you are trying to find the uncertainty in x by y. Then you can ask, okay, what is the largest value of x by y? That would happen when x is overestimated and y has got the smaller value. You have actually measured the lower value of y, right? And then if you can expand this and neglect, products of uncertainties, etc. And then what you would get is that the fractional uncertainties actually add up. So you can show for products and quotients that the uncertainty, they add up like this. Okay, once again, you can show this, but then using the fact that they are independent measurements, you will have to say that this is actually under root of the sum of these fractional uncertainties. This happens most of the time when you have some, for example, when you have, yes, the other day Rajaram was talking about how, I suppose, length is, the unit of length is standardized. So the unit of time comes with some lot of accuracy coming from that cesium clock, but then you assume that C is constant, and you can find out, okay, now what is the uncertainty in the length, right? So this happens, yeah. So I'll sort of go ahead with this because I want to get to some points, all right? And we can talk about any doubts you have later. All right, so here's an example, and here what we are doing is we are just making independent measurements of length and finding out the mean, which is basically the sum of all these measurements. And so the individual uncertainties are going to add up using that formula that I wrote the other somewhere else, just delta x square plus delta y square. Here I have 3, so you have all of them being squared and added up under the root, and the final uncertainty ends up being 0.173 centimeter, which when rounded off gives you 0.2 centimeter. Okay, just an example. Yeah, so here is what I told you about products and ratios. But I just want to point out that for that formula over here, I mean, right now I'm just writing it as a formula, but you can reason it out. I don't want you to mug it up or anything like that. It's quite easy to see. You can use some principles of calculus, and you can see that if you have any general function of x and y, the combined uncertainty can be calculated using the partial derivative of the function with respect to x and respect to y. Okay, and you get these answers. All right, so maybe I'll leave this out. We can go to the next one where I'll ask you to, okay. So let's look at these. I've just given you a few functions of x, basically a quantity which comes from, you measure x, but then the quantity you actually want to find out is q, okay? So how does the uncertainty propagate from x to q? So that's something that we can find out. So in the first case, what do you think? Q equals kx. How do you think the uncertainties? So Q equals kx, right? So what do you think delta Q should be? How is it related to delta x? Okay, fine. This is k delta x. Okay. The more customary way of writing this is to divide this equation by this, and what you get is delta Q by Q. The fractional uncertainty is actually equal to they're equal to each other. You see that the fractional uncertainties are equal to each other, right? So you want to get rid of, you just want to see how the values are related, uncertainties are related to the mean values and the other uncertainties and no constants in between. What about x to the n? Want to try that out? How does delta Q, how would you get delta Q from a measurement which is x to the n and has that delta x? It's very simple to do. All of you are so good at calculus, you can do it within no time. What do you think? Delta Q by Q equals n into delta x by x. Okay, so maybe you guys can check that out. E to the x. Log Q, a lot of logs are going around, right? So this is important. What do you think? Work it out, no? Put pen, paper, circuit works. Work it out and see what you get. How is delta Q related to delta X when is E2? That's 2. Okay, so let's maybe, so it's not just that, but you can, n next to the yeah, delta X, that's right. But then you can divide it by Q. So that gives you delta Q by Q equals n delta X by X. Okay. I'm going to leave this to you guys to do, okay? Maybe there's some more problems in the evening you can work on. I want to get to a specific point which you will need in your experiments, and I'm afraid we are running out of time. So I just want to get to that point. Yeah, I know everyone knows least squares fit. Everyone knows least squares fit? Yes. People here who don't know what it is, don't feel shy. You don't know? Okay. So I'll tell you roughly what a least squares fit is, okay? So how do you go about doing it? So often when we are doing experiments, we have one independent variable which we are fixing, and then we find out when you fix that, what is something else, and we plot a line. Most often we are plotting lines, or we polish the data in such a way that it becomes a line. Right? And then at the end of the day, what our job is to find the slope or the intercept or whatever of that line. Right? So we need to find the best line which represents the data in a faithful manner. So the way to do that is to calculate this quantity S, which is, so suppose there's this M and there's this B, which basically characterize our perfect line, then the predicted value of Y, given a value xi, the predicted value of Y should be mxi plus B. So the difference between the actual value and the predicted value is a measure of the error. So all you have to do is add up all these errors, the square of the errors, right? And the best fit would be that line for which the square of these errors is the smallest. That's the logic. So this is a quantity S, which you want to minimize. With respect to what do you minimize? What are the things which are changing? What? Huh? What values? No, you can't change the observed values are the observed values. What are the things that you want to change to get the ideal line? No, the only things you can change for a line are the slope and the intercept, right? So those are the things which you keep varying the slope and the intercept, and you find that combination of slope and intercept which gives you the smallest value of S, right? So M and B are actually the ones that you're tuning in this minimization calculation. So you take that S and you find the partial derivative with respect to M, find the partial derivative with respect to B, and equate them to 0 because you want the error to be a minimum with respect to any change in slope or intercept. You want to find those slopes and intercepts for which this is a minimum. Okay, and then the answer is very easy to get. You can work it out very quickly in your notebooks. You'll find that you get a expression for M and B in terms of the data points that you have, which is amazing, wonderful. You have X's and Y's, everything is known. All you have to do is, however complicated this may be, it doesn't matter now, we have computers and they can calculate whatever we want. And we can basically calculate the slope and intercept, right? So this is a standard experimental procedure. And if you ask Google Sheets or any other thing to do a best fit, basically this is what they would be doing. But some of the questions are like, okay, now calculate that's not where it ends. Often the slope of a curve is the thing that we want to measure. We want to measure what is resistance, measure voltage, current, that's fine. But I need to know, I know, okay, the uncertainties in voltage and current. How do you find the uncertainty in the slope? You need to find the uncertainty in the slope. How sure are we that the slope is exactly this value? How sure are we that the intercept is exactly this value? And this intercept is, there are several experimental examples that I can give you where the intercept is the point of the experiment. Some most famous, anybody knows some really most famous examples of experiments where the intercept is actually the thing that you want to find. H by E. Ah. Okay. Okay, in the classical world, the Charles's law experiment is one of those things where the absolute zero is basically found by extrapolating a graph and finding out the x-intercept. So there you need to know, how do you find the uncertainty in the intercept, right? So how do you think you would do it? How do you find the uncertainty in M and B? What do you think? Just think of it, okay, there are all, I know I'm sort of compressing a lot of things in one lecture because I feel that you guys need to know these things in order to do the data analysis for your experiments. But, you can also go, it's a lot to do in one lecture. So you can also go and read, but suppose I give you this problem. I say, look, M and B are given by this. I want to find the uncertainty in M and B. Then what would you do? How would you go about it? What do you think? Common sense, what do you think? Forget calculations. What does common sense tell you? You somehow look at your graph and you take the maximum and the minimum, take like this highest possible slope that you can possibly get with any two data points, and then the lowest possible slope that you can get with any two data points. Okay, that is a good estimate of the very, if you had only taken those two measurements, you would have gotten those slopes.
Since intercept is dependent on the slope, can we say that the uncertainty of the intercept is the same as that of the slope?
Yeah, actually no, it's not the same, but they are related. Yeah, so you can take the lowest possible slope and that would give you the highest possible intercept, right? And similarly, and then you could find out, oh, it is actually cutting between this point and this point on the y-axis. Maybe that is my uncertainty in intercept. That is acceptable. That's fine. If you're using your common sense and reporting an uncertainty, I think that makes sense. Okay, but of course, least squares gives us a slightly more exact picture. So there is a way in which to do this, and this is also by propagating uncertainties. Okay, so the formula, the way to do, the operational way to do it is like this. So we are going to assume that since we are actually fixing, in an experiment, we are fixing the x-axis, we are fixing the x values and measuring y, we are going to assume that the uncertainties in x are negligible compared to the fractional uncertainties in x are negligible compared to the fractional uncertainties in y. Okay, so if we say, okay, 1 centimeter, 2 centimeter, we better be sure that we are fixing it to, to validate basically this assumption. Okay. Often this is not the case, and then you would have to do a more complicated calculation. So if you make that assumption, then you can just use these formulae for the slope and intercept, and this is the scheme I gave you, right? You take the derivative with respect to y and basically multiply it by delta y, square it and add them up. That would give you the uncertainty in the slope. And then again, we are making another assumption that delta yi is equal to delta y. What does this mean?
The uncertainty in every value of I for the y is the same.
Yeah, that it doesn't depend on the value of y. So is it true all the time? Is the uncertainty independent of the value of y? Not all the time. In some cases, the higher y is, especially if you have exponential functions and all, you would see that the uncertainty depends quite a lot on the value. So again, this is a sort of a shortcut, but it gives you a good handle on uncertainty of the slope. So if your condition, if you can justify that delta x is negligible and the uncertainties in y are independent of the y values, then you can say that, look, the uncertainty in the slope is something that I can calculate exactly. Okay, and it only depends on the uncertainty in y. And similarly, there is a method that you can go and follow for C. So these are right now formulae, and you can use them as formulae or whatever. When you're doing your calculations, I think many of you have to find the uncertainty in slope and things like that. So see if these conditions are valid, and then you can, measure the uncertainties. Okay, so I think that's all I have for today, and I've finished. Miraculously, I have finished exactly on time. So let's have some questions, more questions. Okay, so good luck with all your error analysis.